Imagine for a second that you were staring at a computer monitor,
Okay.
and on that screen is your primary operations dashboard.
Right, the one you're always watching.
Exactly. And it's supposed to be this comforting sea of green lines, showing healthy, continuous traffic on your company's core e-commerce site.
Which is the dream.
That's the dream. But right now, it is painting a very, very different picture.
Oh, no.
Yeah. A massive, terrifying spike of red is rolling in. You are looking at a tidal wave of HTTP 500 errors.
Wow. Just the worst case scenario.
It really is. And, just to put that in context for anyone listening, an HTTP 500 is an internal server error, which basically means your back-end process is completely panicked.
It just threw its hands up and quit.
Yep. Crashed and abruptly severed the connection with the user.
Yeah.
And in this scenario, for 4 agonizing minutes, every single active user on your platform, 100% of them is experiencing a total checkout failure.
That is brutal. 4 minutes in e-commerce feels like a lifetime.
It's an eternity. Their carts are crashing. The company is literally bleeding revenue by the second. And the absolute worst part of this whole situation.
Let me guess. You're the one who pushed the code.
You were the one who just merged the pull request that caused it all.
Yeah. That's the ultimate pit-in-your-stomach moment for anyone who works in platform engineering.
Oh, for sure.
Time basically just stops when you realize your automated deployment pipeline just broke production for every single user hitting the site.
It is a profound nightmare. But today, our mission is to explore how we engineer systems so that you never actually have to live through that specific nightmare.
A very worthy mission.
Right. We're doing a deep dive into this really excellent piece by Aaron Rose over at tech-reader.blog. It's called The Secret Life of AWS Canary Deployments.
It's a fantastic breakdown.
It really is. We're going to systematically break down how to limit the damage of a bad code release using automated traffic shifting.
Because, let's face the reality of software development here. We are all going to deploy bad code eventually. It's just a fact.
Exactly. It's inevitable.
Yeah.
But we're going to learn how to make your deployment automation safe. So that a subtle mistake doesn't cascade into this, catastrophic outage.
Right.
And Aaron Rose sets this all up with a really relatable narrative. He talks about a developer named Timothy who accidentally breaks the checkout microservice.
Poor Timothy.
Right. And his DevOps colleague, Margaret, who sort of steps in to introduce him to a much more resilient architecture.
It's a brilliant framing device, honestly, because it highlights this super common paradox in modern CI/CD.
Which is continuous integration and continuous deployment for those following along.
Exactly. And the paradox is that Timothy actually did exactly what he was supposed to do.
Right.
He wrote a new feature, he merged it, and his automated pipeline picked it up, ran the unit tests, and deployed it to production in a matter of minutes.
Yeah, he thought he was crushing it. His pipeline was lightning fast.
But his system failed so spectacularly precisely because his automation was, well, it was actually too fast.
Too fast and completely lacking any boundaries.
Right.
He merged a feature with a subtle, logical bug. Like it was the kind of edge case bug that unit tests just frequently miss.
Because unit tests typically mock the database. They run in total isolation.
Yeah, they don't accurately reflect how concurrent requests behave in a wild, highly trafficked production environment.
They never do.
And because his pipeline utilized what we call an all-at-once deployment strategy, it instantly replaced the entire production Lambda function.
Okay, so let's unpack this for a second because an all-at-once deployment strategy is exactly what it sounds like.
Right.
But it really helps to understand what is physically happening at the infrastructure level here. In a traditional immutable deployment, you aren't just updating a few files on a server.
No, you're doing way more than that.
You are completely replacing the underlying compute resources. When you deploy a serverless function like an AWS Lambda, for instance, all at once, the cloud provider takes your new code bundle, updates the function's configuration, and instantly begins spinning up brand new execution environments.
With the new code.
Exactly. Containing your new code while simultaneously terminating all the old execution environments.
So there is absolutely zero overlap.
Zero.
The system cuts the cord on the old stable environment and just entirely commits to the new untested environment in a matter of seconds.
It's a leap of faith.
It's like, okay, imagine a restaurant, right?
Okay.
Right in the middle of the Friday dinner rush, like 7 p.m.
Packed house.
Packed house. And the manager just decides to swap out the entire kitchen staff
Oh, wow.
and the menu right there on the spot.
Yeah.
If that new staff doesn't know what they're doing, or the new menu is flawed, every single customer in that restaurant suffers instantly. There's no backup plan.
That is a perfect analogy. Because if that new environment has a fatal flaw, say, I don't know, it can't parse a specific JSON payload correctly, every single request hitting your API gateway immediately fails.
Yep. The whole kitchen goes down.
Exactly. There's no fallback capacity. And this brings us to Margaret's point in the piece, which I think is a foundational concept in cloud architecture.
The blast radius.
Yes. Margaret actually tells Timothy, automation is powerful, but speed without safety is a liability.
Speed without safety is a liability. That is such a great quote.
It really is, because she's talking about the blast radius. In system design, the blast radius is defined as the maximum percentage of users or the maximum percentage of a system's functionality that is impacted when a specific component fails.
And when you execute an all-at-once deployment, you are intentionally maximizing your blast radius.
You're dialing it up to 100.
Right. By swapping out the entire compute layer instantly, a single fatal bug achieves a 100% blast radius. Everyone goes down.
And it really makes you stop and think about the infrastructure you interact with, or build every day.
Absolutely. If you are listening to this right now, take a second and evaluate your own deployment pipelines. Are you currently operating with a 100% blast radius?
Because if you are, you're essentially walking a tightrope without a net.
You really are. The overarching goal of modern release engineering is to shrink that radius down to the absolute smallest mathematical fraction possible.
Which is exactly why the industry has shifted toward this concept of the Canary release.
Which, by the way, is such a great historical callback.
It is.
For anyone unfamiliar with the terminology, it borrows an old survival tactic from 19th century coal miners.
Right. They used to carry actual canaries down into the mine shafts.
Yeah, because canaries have a much faster metabolism and respiratory rate than humans, so they're highly sensitive to toxic odorless gases.
Like carbon monoxide.
Exactly. If the canary stopped singing or collapsed, the miners had this early warning system. They knew a localized failure was happening, and they could evacuate before the gas reached lethal levels for them.
And the architectural equivalent operates on the exact same premise. Early detection and contained risk.
So how does that look in software?
Well, in software, a canary release dictates that instead of routing 100% of your production traffic to your newly deployed compute instances immediately, you isolate a very small fraction of that traffic.
Like, say, 10%.
Exactly. You shift only that 10% to the new version of the code, the remaining 90% of your active users. They are completely untouched.
They don't even know anything is happening.
Nope. The infrastructure continues to route them to the older, stable version of the code that you already know handles production loads perfectly.
Okay, I hear the argument for canary releases shrinking the blast radius of errors, but let me push back on this for a second.
Sure, go for it.
Because aren't we essentially still releasing buggy code to live users? I mean, isn't it inherently bad that 10% of actual human beings are getting HTTP 500 errors?
That's a really fair question, and it's something a lot of developers struggle with at first. But you have to look at the philosophy behind it.
Which is what?
That bugs are simply inevitable. You cannot catch everything in staging.
Yeah.
So yes, 10% of users might experience an error if the new code is completely broken, but limiting exposure is the key.
Better 10% than 100%.
Exactly. A total failure now only affects a small fraction of users for a very brief window of time, rather than taking down the entire platform.
Okay, that makes sense. It's damage control.
It's purely damage control.
Right.
And the source material also details an alternative that Margaret mentions, which is the linear deployment strategy.
Oh, right.
Instead of shifting 10% all at once and just holding it there, a linear deployment shifts traffic in equal gradual increments.
Right. So like shifting 10% of traffic every single minute.
Exactly. It gives you this incredibly granular step-by-step confidence curve.
Okay, so the theory is incredibly sound. Shrink the blast radius,
Yeah.
use a canary or a linear shift, and physically protect 90% of the active users.
Yep.
But here's where it gets really interesting for me.
How so?
Like, how on earth does a cloud environment actually execute this mechanically?
the nuts and bolts.
Yeah, shifting exactly 10% of users sounds great on a whiteboard, but in reality, you have thousands of asynchronous requests flying into your API gateway from all over the world every single second.
It's chaotic.
It is. How does the infrastructure physically divide and route those packets?
That is where we have to dive into the specific tooling, namely AWS CodeDeploy. Aaron Rose's piece breaks down the mechanics of this beautifully.
He really does.
CodeDeploy is a fully managed deployment service, and it basically acts as the orchestration engine. In the narrative, Timothy's checkout service is built on a serverless architecture using AWS Lambda. So to make this fractional traffic shift happen, AWS relies on the interplay between two specific mechanisms: Lambda versions and Lambda aliases.
Okay, so the way I like to conceptualize an alias, tell me if this tracks, is by comparing it to a physical train switch track.
I like where this is going.
So in this scenario, the infrastructure, the actual serverless compute environments, are the train stations at the end of the tracks.
Okay.
When you publish a Lambda version, AWS creates an immutable snapshot of your code and gives it a unique identifier.
Right, an Amazon resource name, or ARN.
Exactly. So you have version 1 sitting at the end of track A and version 2 sitting at the end of track B. Both exist simultaneously.
Exactly. The versions themselves do not control who visits them. They are just destinations.
Right, they're completely passive.
Yeah.
The Lambda alias, on the other hand, is the switch track itself. It's located way up the line where the traffic first enters.
Yep.
The alias has its own static ARN that all your client applications talk to. And AWS CodeDeploy is basically the automated switchboard operator.
It's the traffic cop.
The traffic cop. CodeDeploy updates the routing configuration on that alias. It mathematically weights the switch. It says, for every 10 requests that come down the pipe, physically lock the switch to track A for 9 of them, sending them to version 1.
Right.
But for the 10th request, flip the switch to track B, routing it to version 2.
It's a fantastic analogy. CodeDeploy handles all that mathematical weighting natively. When the pipeline triggers, it applies a specific deployment preference.
Like what?
Well, in Margaret's configuration, she uses one called Canary 10% 5 minutes.
Very descriptive.
Exactly what it says on the tin. CodeDeploy provisions the new Lambda version 2, leaves version 1 fully operational, and updates the routing weights on the alias to 0.9 and 0.1.
90-10.
Right. And then the system enters a holding pattern. It waits for exactly 5 minutes to see how the new environment handles that 10% load.
But it's crucial to note for our listeners that this exact traffic shifting philosophy isn't limited to just serverless functions.
Oh, definitely not.
CodeDeploy executes this exact same pattern if you are running containerized microservices on Amazon ECS, or even legacy monolithic applications on traditional EC2 virtual machines.
The underlying mechanism just changes slightly.
Right, like instead of manipulating a Lambda alias, CodeDeploy integrates with your application load balancer.
Your ALB. And an ALB uses concepts called target groups. You would have a blue target group containing your old containers and a green target group containing your newly deployed containers.
Oh, the classic blue-green setup.
Exactly. CodeDeploy dynamically modifies the listener rules on the load balancer itself, instructing it to forward 90% of incoming HTTP requests to the blue target group and 10% to the green target group.
So the implementation details vary, but the architectural outcome, a strictly enforced 10% blast radius, is totally identical.
Identical.
And during that 5-minute holding pattern, your engineering team isn't just sitting around crossing their fingers, right?
Well, hopefully not.
This is where the observability stack becomes hypercritical. The source material specifically highlights the integration of AWS X-Ray, which is a distributed tracing service.
Right, because when you are running a Canary, traditional logging isn't always enough. Your logs are suddenly a messy mix of two completely different code bases.
Yeah, good luck reading that JSON dump.
Exactly. You need to be able to isolate the signal from the noise. And AWS X-Ray solves this by injecting a unique trace ID into the HTTP headers the moment a request hits the API gateway.
Oh, wow. So it tags it right at the front door.
Right at the front door.
Right.
And that ID follows the request all the way down to the stack, through the Lambda function, into the DynamoDB queries, and out to any third-party payment APIs.
Which means developers can bring up a visual service map, and they can actually filter the telemetry data by the Lambda version annotation.
It's incredibly powerful.
You can sit there and visually compare the latency distribution, like, your P99 latency of your 10% Canary group, directly against the baseline of your 90% stable traffic in real time.
Side by side.
Yeah. You aren't just looking at a generic dashboard of red lines anymore. You are comparing the structural integrity of the new train track versus the old train track down to the millisecond.
It provides incredible granular visibility, but this actually brings us back to the core problem of Timothy's bad code.
Right. The bug.
Let's say that new code does contain a fatal bug. It starts throwing those HTTP 500 internal server errors, If that bug strikes the 10% canary group, we have a localized failure.
Which is better, but still a failure.
Right. But for an automated rollback to work, the deployment service needs to be tightly coupled with that observability stack we just talked about.
You can't just wait 5 minutes blindly.
And you certainly can't rely on human reaction time.
Oh, absolutely not. I mean, even if I'm staring intently at the X-ray service map, by the time my optic nerve registers the spike in errors,
Takes a second.
then my brain realizes it's the version 2 canary causing it. Then I got to tab over to the AWS console, authenticate, find the deployment execution, and manually click abort.
Thousands of checkout requests could have already failed.
Exactly. Humans are far too slow for cloud scale traffic.
Which is why we have to rely on the ultimate safety net. Automated rollbacks.
Machines fixing machines.
Exactly. We need machines to fix machines. And this requires a deterministic, rule-based trigger. In the architecture outlined in the piece, this is achieved by defining a CloudWatch alarm.
Specifically named the checkout error alarm.
Yes,
Yeah.
and Margaret deeply integrates it directly into the CodeDeploy configuration file.
So CloudWatch is continuously calculating the error rate specifically for the requests hitting the new Lambda alias dimension.
Precisely. CodeDeploy is not just passively waiting for the 5-minute timer to expire. It is actively, continuously polling the state of that specific CloudWatch alarm.
Wow.
The moment the new code throws enough HTTP 500 errors to breach the defined statistical threshold, the CloudWatch metric spikes, and the alarm transitions from an OK state to an alarm state.
And that state change is the trigger.
The very millisecond that alarm trips, CodeDeploy springs into
It
action.
doesn't wait.
It instantly aborts the deployment process. It overrides the routing weights on the Lambda alias, shifting the traffic from a 90-10 split back to a 1,000 split.
So it instantly stops sending requests to version 2.
Yep, routing every single user back to the stable version 1.
And the developer who pushed the code, Timothy, in this case, doesn't have to lift a single finger.
Zero human intervention.
That is the holy grail of release engineering. The developer doesn't have to panic. They don't have to frantically type git commands in a terminal to revert commits.
No stressful hotfixes.
Exactly. They don't have to wait 10 minutes for a new CI/CD pipeline to build a hotfix and push it out. The system detected the anomaly, strictly contained the failure within that 10% blast radius, and basically self-healed by reverting the traffic flow.
And honestly, the most important metric of all in this scenario.
Go that.
90% of the users on the platform never even realized a massive breaking bug had just been deployed to the infrastructure.
They were totally oblivious.
Their HTTP requests were cleanly resolved by the old code, and their checkouts went through perfectly.
That level of resilience provides incredible peace of mind for engineering teams. But what if the reverse happens? Like if the code is actually flawless?
Ah, the happy path.
Right.
Well, if the 5 minutes pass and that checkout error alarm remains in the green OK state, CodeDeploy simply assumes the canary survived the coal mine.
It lived.
It lived. It mathematically assumes the new compute environment is stable under production load, and it confidently shifts the remaining 90% of the traffic over to version 2.
And then it just formally marks the deployment as successful.
Exactly. It's fully automated from start to finish.
So what does this all mean for you, the listener, as you design and maintain your own technical ecosystems? I mean, it requires a fundamental paradigm shift in how you view your infrastructure.
It really does.
By utilizing intelligent routing, targeted observability alarms, and automated rollbacks, your CI/CD pipeline stops being just a dumb delivery mechanism that blindly shoves compiled code out the door. It transforms into a self-healing, risk-mitigating safety net.
That is the core takeaway here. Whether you are managing vast fleets of microservices, maintaining legacy monoliths, or even designing complex internal business workflows, you have to obsess over your blast radius.
Obsess over it?
Building automated safety nets that can detect failure and revert state faster than humanly possible is the defining difference between a fragile system that pages you at 3:0 a.m.
Which we all hate.
and a resilient system that handles failure gracefully while you sleep.
It all comes down to designing for failure, really. Because failure is the only absolute guarantee we have in software engineering.
It is entirely inevitable, but there is one final lingering architectural dilemma in Aaron Rose's piece that I think takes us entirely to the next level.
Oh, right. The final twist.
Yeah. After all this sophisticated automation is set up, the narrative poses this brilliant, really perceptive question.
Let's hear it.
What if the Canary deployment succeeds perfectly? The 5 minutes pass without a single HTTP 500 error. The alarm stays green, and the new code goes fully live to 100% of users.
High fives all around.
Right. But what if that new feature contains a subtle business logic flaw that doesn't trigger server crashes, but, say, miscalculates monthly subscription renewals a week later?
Oh, wow. Yeah, because from an infrastructure perspective, the deployment phase is completely finished.
It's done.
CodeDeploy did exactly what it was told, marked the release as a success, and terminated the process. A 5-minute deployment monitor looking for server errors has absolutely no way to detect a silent logic bug in a database calculation days later.
Exactly. CodeDeploy only protects the infrastructure release. It doesn't know about business logic.
That's a huge distinction.
To protect the product release, the source material briefly introduces the ultimate decoupling strategy.
Which is?
Feature flags. It suggests that to achieve true, uncompromised safety, engineering teams must entirely separate the concept of deployment, which is simply the act of pushing code binaries to a server, from the concept of release.
And release is the act of exposing a new feature to the end user.
Exactly. Decoupling the two.
Decoupling deployment from release. That is an incredibly powerful architectural concept for you to chew on and research on your own.
Highly recommend looking into it.
Like, how might you architect your application to safely install a brand new, highly complex feature into your production environment today, but leave it completely dormant, waiting until next month to actually flip a Boolean switch and turn it on for a select group of users?
It completely changes how you manage risk.
It really does. It just goes to show that there is always another layer, another pattern to uncover when learning how to build truly bulletproof systems.
Always something new to learn.
Because at the end of the day, no one wants to be the person staring at a dashboard, watching a massive spike of errors roll in,
Right.
knowing they just broke the experience for every single user.
Nobody wants that job.
Nobody. So take the time, architect the safety nets, enforce backwards compatibility, and let the canaries do their job.